now we are going to modify our exponential growth and decay models. So we will start by adding a drug intravenously. So the concentration of a drug in a person, C of t, continues to decrease at a rate proportional to the current concentration of the drug with a constant of proportionality k equals negative 0.12. From that information, we would have that dc dt was equal to negative 0.12 C. But now the concentration starts at 8 millimoles at 2 p.m., but 0.5 millimoles of the drug are added to the person's body every hour. So we want to represent that in the differential equation. Well, if the drug was not being absorbed, we could simply say that dc dt was equal to 0.5 millimoles, so that the derivative, the rate of change, was a constant increase of 0.5 millimoles. But because the drug is being absorbed, we are going to say that dc dt is equal to negative 0.12 C, and then add to that the 0.5 constant rate of increase of the drug in the person's body. Again, we will say the initial concentration is 8 at 2 p.m. And so now this is a slightly different kind of differential equation than the one we had before, because now instead of the derivative just depending on the constant or the concentration C, it also, we are adding the drug at a constant rate of 0.5. Instead of trying to figure out how to solve this problem, I'm going to give you the solution, and we're going to verify that that is the solution so that we can then use that information to help us come up with an informed way to solve this differential equation. So I want to show that C of t equals 1 over 0.12 times 0.5 minus 0.46 e to the negative 0.12 t solves that initial value problem. The way I'm going to do that is I'm going to take the derivative, dc dt, which in this case is the derivative of 0.5 over 0.12, or 0. And then it's the derivative of 0.46 over 0.12 e to the negative 0.12 t, which is itself times negative 0.12. And so the derivative is 0.46 e to the negative 0.12 t. Now we need to show that that's equal to negative 0.12 times the function c plus 0.5. So we will do negative 0.12 times the solution, which is 1 over 0.12 times 0.5 minus 0.46 e to the negative 0.12 t, and then we will add 0.5. So we've substituted in our solution for C. We see that the 0.12s cancel here, okay? And we get that negative 0.15 or 0.5 plus 0.46 e to the negative 0.12 t plus 0.5. And we see that the negative 0.5 and the positive 0.5 cancel, and therefore negative 0.12 c plus 0.5 is just 0.46 e to the negative 0.12 t, but that matches what we got for the derivative, and therefore the proposed solution that I gave you is actually a solution to the differential equation. We also want to note that C of 0 needs to be 8. So C of 0 in this case is going to be 1 over 0.12 times 0.5 minus 0.46 e to the 0. that's going to give us 1 over 0.12 times, in this case, 0.04. And if you plug that into your calculator, you will get 8. We can now ask what happens to the concentration of this drug as t goes to infinity. So we can look at the limit as t goes to infinity of c of t, which is the limit as t goes to infinity of that function, 1 over 0.12, 0.5 minus 0.46, e to the negative 0.12t. And we see that this exponential decay will go to 0 as t goes to infinity, and we're left with 0.5 over 0.12. So what happens as t goes to infinity? Well, the concentration no longer goes to 0 like it did in our previous problem, but instead the concentration is going to a finite number. So the concentration approaches a constant, and that constant is approximately 4.167 millimoles. And so we see that this patient with this intravenous drug being pumped into them, right, has this constant amount of the drug in their system for all time. They'll have some sort of constant buzz for a while. Now, a good question that you might want to ask is, what would happen if our initial concentration had been 0.5 divided by 0.12? So what if the initial concentration had been that value that the concentration approached in our previous solution? Well, one way we can see that is we can ask, well, what would dc dt be in that case? What would the derivative be? And it would be 1 over, it would be negative 0.12 times c. C in this case would be 0.5 over 0.12. And then we would add 0.5 because that is our equation for the derivative. And you'll notice that because these 0.12s cancel, we get negative 0.5 plus 0.5, so we get 0. So the derivative would be 0 when the concentration is at that limiting value that we had before. So this value of 4.167, or 0.5 divided by 0.12, is the value of the concentration that makes the derivative 0, where there's going to be no change. So in essence, that value that you see there is some sort of equilibrium. And we will discuss that further. We could also modify our population growth example by, instead of just allowing a population to increase without bound, we might have the population of a town, say in thousands, that grows at a rate proportional to the current population with a constant proportionality k equals 0.25. But for that town, maybe approximately 1,000 people leave the town per year. And so we would still have that the rate of growth is proportional to the current population, 0.25 times p, but people would be leaving at a constant rate, that constant rate being minus 1,000. Again, we'll have some sort of initial value, p of 0 equals p sub 0. And this would be an initial value problem that would describe a population where there's growth, but there's some sort of people leaving, an emigration. Okay, both of these two problems that we just solved have a particular form. It is that the derivative, dy dt, is equal to a constant times y, but we're going to add another constant, rate, b. So the constant a, okay, is going to be that constant of proportionality. So that's going to be the growth or decay rate. And the constant b is going to be a constant increase or decrease in the quantity that we want to represent. Now you should see from the previous example with the concentration of the drug that our solution had a form of a constant times e to the at plus another constant d. So this would be a good guess for the solution of our differential equation. Before, when we didn't have the constant b in our differential equation, the solution was just ce to the at. So we could reasonably assume that maybe if we add a constant increase or decrease, that would add some sort of constant to our solution. Now, if we're able to plug this solution back into the differential equation and get that it satisfies the differential equation, then we'll know that this is actually the solution. So that's exactly what I'm going to do. I'm going to take the derivative of the solution. The derivative is going to be a ce to the at. The derivative of d, of course, is 0. And then I'm going to see what happens when I look at ay plus b. So that's a times our solution, ce to the at plus d, and then plus b. So that's a ce to the at plus ad plus b. And I want to note that these two quantities are supposed to be equal to each other. I could start matching terms and notice that ace to the at matches this ace to the at. And so that leaves me with the fact that ad plus b must equal 0 in order for the left and right hand sides of the differential equation to match. So that tells me that ad plus b is 0, and that says that the constant d must be minus b over a. Now I've figured out what the constant d would be in this situation, but what about c? I can use the initial value to figure that out. So y of 0, okay, is going to be a c e to the 0, okay, plus d. Okay, but d we just figured out, so I'm going to say that that's minus b over a. And then we know that that's supposed to be some initial value, y0. Well, since e to the 0 is just 1, okay, so I've made one slight mistake here. So I'm going to just go back and erase that a, because y of 0 is supposed to be c e to the 0. So that comes from this solution, c e to the 0 plus d, d being minus b over a. I'm setting that equal to y0. Okay, so that tells me that c in this case is supposed to be y0 plus b over a. And so the general solution to the initial value problem, dy dt equals ay plus b, and y of 0 equals y sub 0, is that y of t is equal to y0 plus b over a, e to the at, minus b over a. And you'll notice that the solution that we got, or that we verified for the concentration of the drug problem at the beginning of this video, does have that exact same form. we can now ask what happens as t goes to infinity for the solutions to this equation. Well, if a is positive, then y, in this case, will go to infinity because that positive exponential will continue to grow. Okay, but what happens if a is less than 0? Well, if a is less than 0, then we get that y will go to minus b over a because that exponential will then decay. And all I'm left is minus b over a. So what's so important about that value, maybe minus b over a? What happens if my initial value was minus b over a? Then y of t would equal, let's see, so minus b over a plus b over a e to the at minus b over a. And so y of t would remain at minus b over a for all time. So if we start at this value minus b over a, then we will continue at that value minus b over a for all time. Well, what's the derivative at that point? Well, dy dt is a y plus b. Well, that's a times minus b over a plus a. So the derivative is 0. So if we start at minus b over a, the derivative is 0, and it remains 0 for all time, which explains why our function y of t remains at minus b over a for all time. See, y of t being minus b over a is called an equilibrium solution. Equilibrium meaning no change. So if we think back to that concentration of a drug problem, we're going to say if we start at some concentration, minus b over a, then we're going to remain at that concentration for all time. And that is equilibrium. I want you to note that if b is 0 in the problem above, so we just get rid of that b there, then we have the exponential growth and decay problem that we had before. And in that case, the equilibrium solution was 0. And we discussed that before. If you start with a 0 population, it can't grow. If you start with a 0 concentration of a drug or a 0 amount of a chemical, it can't decay because it's already at 0. One final note that I do want to mention is I said that if a is bigger than 0, y does go to infinity. Well, that really does depend on whether what's in front of the exponential is positive or negative. So if what's in front of the exponential is negative, you'd get minus infinity. So I would say if a is greater than 0, then y can go to plus or minus infinity. And we'll see with the example that we do tomorrow what the implications are of that.